ultimately, the goal of this activity is to get us thinking about equivalence. And equivalence in the sense of equivalence relation, this topic that you probably spend a great deal of time thinking and worrying about in Math 180 when you're first learning how to prove and learning how to work with sets and that kind of stuff. Equivalence relations are a pretty big deal. They're actually going to be our gateway drug into the sort of rigor of abstract algebra. So I want to get us there, at least get a taste of it before we wrap up today. But to get that started, what were some of the things you noticed as you took a number and then took a trip around the clock by adding that number to itself repeatedly? So did you notice any patterns? Which numbers did you visit during your trip? Which k's visit the same set of numbers? What were some of the patterns that emerged? So one of the first things that you said you noticed was that this table has a symmetry to it, right? That if I start in the middle at 6, if I take a step to either direction, I'm going to get the same. Okay. Can we express that symmetry using a formula? 5 and 7 correspond. 4 and 8 correspond. 2 and 9 correspond. How are those corresponding elements related? That holds a lot of the time, except when what? Except when what's 12? Actually, I think it's also when f of k equals 12. You end up with a problem, don't you? But yeah, so this equation, which you could solve to get f of k equals 12 over 12 minus k, that seems like it holds for many of these values of k, but not all of them. So how do we patch up that issue? What I was kind of going for here also is that symmetry that Caitlin describes can be described with the same kind of 12 minus k thing. F of 12 minus k is the same as f of k for these examples, right? That 8 takes the same number of steps around the clock as 12 minus 8, which is 4, right? And so on and so on. And then when k is equal to 6, this doesn't tell us anything interesting other than f of 6 equals f of 6, because of course it does. But yeah, so there's a symmetry there. Some mathematicians call this a functional relation. The Riemann zeta function, the subject of the Riemann hypothesis, has a symmetry equation that looks very much like this one. So finding symmetries like this is a big deal. Okay, so what are some of the other patterns or things that you noticed or other things that you wondered about this so far? You noticed that all of the values of f of k were factors of 12. All of them divide evenly into the number 12. So let me write that observation down here. All f of k are factors of 12. So the way that we usually write that is with this vertical bar. So this says is a factor of, or divides. So looking at this odd entry out here at the end, right? The question asked you to start at the top of the clock and then add your number repeatedly until you get back to the top of the clock. But if my number is 12, if I was born in December, right, then what happens if I add 12? 12 hours past 12. Well, it's going to end up at 12 again. So certainly I'm back at 12 after one step, but I'm also at 12 after 0 steps. Right? Yeah.
So if it's 0?
So no, your observation here is that when k is prime, f of k reaches its maximum value of 12. So that is certainly true for 5 and 7 and 11. But what about 1? 1 is not. Relatively prime to what? Relatively prime to itself. I suppose 1 is. But I want to hang on to this relative timeless notion, because this is really super critical here. When we say prime, what does prime mean for an integer? Yeah, the only things that are divisible by are itself and also 1. What about relatively prime? When you add the word relatively, what are we doing? Yeah, two numbers together. So A and B are relatively prime if whenever I have a number that divides A and also divides B, so any common factor of A and B must be what? You said it. Right. So the only divisor that's common to both A and B is 1. Or another way to say that is that the greatest common divisor of A and B. So they share no interesting common factors. Two relatively prime integers share no interesting common factors. So can we tweak Noah's primeness observation a little bit to cover all of our cases? In which cases is f of k equal to 12? Certainly when k is prime, but also at least when k is relatively prime to this number. What's playing the role of 0? When k is relatively prime to 12, we maximize f of k. So there's an observation that sort of ties together and in those cases, let's take the 5 example. If f of 5 is equal to 12, what numbers does 5 hit in its trip around the clock? All of them. Let me call that out as a separate observation. That in these cases, all numbers around the clock get visited in our trip around the clock. After all, that's why it takes us 12 steps to get back to the beginning, because I have to visit all 12 of the numbers before I get back to the start, right, in those cases. So 1, 5, 7, and 11 seem to have this kinship with one another. They all kind of have this, we visit every element on the clock before we get back to the top of the hour. So that same symmetry that explained to us the symmetry in the whole table also shows us that there's a symmetry among the relatively prime pairs of numbers, relatively prime numbers to 12, right? 5 and 7 are kind of, they're mirror images of one another. 1 and 11 are mirror images of one another. So we might, if you're taking number theory, you might want to take this as a theorem. Is it true that the GCD of 12 minus k with 12 is the same as the GCD of k with 12? Question mark. Because if both sides of that equation are equal to 1, then we have the pairs of relatively prime examples. But if those expressions are not equal to 1, we still might get, for example, is the greatest common divisor of, what is the greatest common divisor of 4 with 12? The biggest thing that 4 and 12 have in common? 4. What's the biggest thing that 8 and 12 have in common? Also 4. Right? So it seems like this does work for the rest of this table. This might be something that, if you're taking number theory, you might be called upon to prove a statement like that. Right? So I want to close this example and get us at least initially thinking about equivalence relations, making the following observation. So this equation that I wrote down here, 3 plus 3 plus 3 plus 3 equals 12. That's an equation that you would not have batted an eyelash at in second grade, whenever you first learn how to add whole numbers. But some of the equations that you wrote down in this example probably made less sense. For example, what about 9? If 9 was my number, and I took 4 steps of 9 around the clock, I would get something that looks like this. 9 plus 9 plus 9 plus 9 gets me back to 12. Well, how does that make sense? And maybe another way to ask that question is, how can both sides, so both of these equations equal 12, but then wouldn't that also mean that 3 plus 3 plus 3 plus 3 equals 9 plus 9 plus 9 plus 9? The left-hand side of this equals the left-hand side of that? What do you make of that idea? Yeah, I'm trying to be coy about it because not everybody has had experience with modular arithmetic, but that's exactly what this is, right? That's the point that I'm driving towards, is that this is an arithmetic system in which it is okay for us to think of 12, which is what I get when I add 3 to itself 4 times, and 36, which is what I get when I add 9 to itself that many times. It is okay for me to think of 12 and 36 as somehow being the same thing. You made this point actually with the number 60 at one point when you were looking at various examples, right? That all of those things are to be seen as the same. 100 hours on the clock is the same thing as 12 o'clock, which is the same thing as 36 o'clock, which is the same thing as 24 o'clock, which is the same thing as 0 o'clock, right? But if those are all equal to one another, quote-unquote equal, then if I add 1 to them, for example, it means that 13 is going to be the same as, 1, you're right, which then is also the same here as 37, which is the same as 61, which is the same as so on and so on. So clearly these things are not equal as integers, but they are equal on a clock, right? And so what that establishes for us is an equivalence relation. And equivalence relations are a way of taking formerly different elements of a set and grouping them together into categories that we hope are going to behave the same as one another. And so where we're going to pick up with this is we're going to pull on that equivalence relation thread just a little bit more to explore this kind of arithmetic, because this gives us a great setting in which to do abstract algebra, because the numbers are almost familiar, but the operations of arithmetic are just different enough that we're going to be able to get a lot of mileage out of modular arithmetic, both modular addition and modular multiplication, as we go through the semester.